Okay, I'm back.
Can you hear us now?
Yes, I can hear you.
Okay.
I have no idea what was going on. Did you guys have questions on the quiz?
We had talked about me doing it on Thursday.
Okay. All right, well, we'll just wait about 15 minutes until the rest of the folks show up. So if you have any questions, just let me know.
Dr. Chrysler,
Yeah,
when are we going to go over a little in detail about the project? Is that today or?
that is actually Thursday, but I am working on it right now, actually. It's just adjusting all the due dates, but I can give you a short rundown. Have you heard about the project from like previous students or people?
A little bit, like it's just like where you have to build a generator type of dealio.
Yeah, so basically today we're going to start like Faraday's law section, so time varying fields. And then I'll introduce the project on Thursday. And so the project is basically building something that deals with time varying fields, which is basically something that you crank or human power that turns that power into something like your human power into something that turns on a light bulb. So that's basically like a direct application of Faraday's law. Yeah. So the only things that I'm going to do differently this year is compared to last year. Is last year, we were it was like more like full pandemic, so I couldn't really suggest or make people work together in teams. So this year, what I'll do is it'll be optional. So if you want to work in a team, you can have a team member, and if you want to work solo, you can do that. So that's one change. And then the other change is going to be that last year we had like that shortened semester due to I don't know, they kind of like changed some things with COVID and changed when the finals week was, but this year it's presumably it's going to be normal, and so there's kind of going to be like basically one extra week for you to work on the project is what it amounts to. So those are the two main things, but yeah, you'll build this generator and give a presentation. So, oh, and one of the other things last year, yeah, I'll go over all of this in more detail, but one of the days of class this year, I will devote completely to like every team will have to meet with me to tell me where they're doing like with the project and how far they've made it, because there's a couple, I think last year a couple people waited a little too long to finish. So yeah. And then the other thing, we'll go over all this when we start class, but the other thing that I highly recommend, I'm sure you have all seen at least, or maybe are a little aware of the fact that a lot of supply chain stuff is really bad this year. So I will highly recommend that you order, if you are planning to order something to use, like if you can't find any wire or magnets, which are two of the main things you probably want to use, I will definitely recommend that you order those right away, like maybe this weekend or something. So yeah. Yeah, just because some things are taking a while to ship, especially some kind of like, I don't really know what, but some random stuff from China does take a pretty long time right now. But we'll go over that in more detail on Thursday. But certainly, like, my hope for the project is that it's definitely possible to build this whole project with junk, like free stuff that you probably just have like laying around. And so that's definitely possible. But if you can't find that stuff, or you want more specific items to make your design more convenient or whatever, then you can buy stuff, and I would recommend doing that like right away. Hi everyone who's joining us. We're just chatting a little bit about the project. I'm going to give all of the details on Thursday, but just speaking a little bit generally about it. So, yeah. So, yeah. Right now I'm just finishing the like converting all the due dates and everything to the ones for this year and making sure that it all looks good before I release it. So, yeah. Then if you're just joining to, the other thing that you could start thinking about just generally is if you would like to work with someone else, if you'd like to have a 2-member team for the project, then that is allowed this year. But you're also welcome to complete it by yourself. So if you want to work with someone, you could spend the next couple days, you could, reach out or text someone else in the class to see if they're interested, but it's not required. So, yeah. It's definitely doable by yourself or with someone else. So. Anyone have any other questions about it? I'm open to answering questions. I just don't have all the stuff prepared to like show all of you. All right, well, 8:20, so let's get started on the class. So in the class, let's see, pull up the schedule so you can all see where we're at. All right, so it's October 19th. You just handed in homework 6. This week, we are going to switch to electromagnetics. So we're actually going to start looking at time varying fields this week. So we're basically going to put everything together and look at the time varying fields. So this is a common approach in many areas of engineering, which is first you start simple, right? You start with the simplest thing you can. So in this case, in electromagnetics, as the name applies, we have the electrical field and the magnetic field. And we started very simply. We started with the electric field that does not change with time. And so we looked at the electric field that does not change with time and discovered a bunch of stuff about it. And then we went to the magnetic field that does not change with time, magnetostatics. And we saw, okay, turns out, right, there's a lot of similarities between electrostatics, static meaning not changing with time, and magnetostatics. And so now that we've seen what these fields look like when they're not changing with time, we're going to progress from the simple case, right, to the more complex case by adding in the time varying field. So first we looked at one thing that was static, and then we looked at another thing that was static. And now we're going to combine both of them together and look at the case where the time does vary. Okay. So we'll call this section electromagnetics. And the primary equation that we're going to be applying is the Faraday's law. So you've probably seen all of, you probably saw some of this in physics too, and maybe in one of the other classes, possibly, maybe a power class, you might have covered some aspects of this. But we're going to look at it in more detail. We'll solve a number of problems where we apply Faraday's law. And then at the very end, one of the last things we're going to look at is this idea of displacement current. And basically, right, we have these 4 Maxwell's equations, and we're able to unify them with this idea of displacement current, which says that if you change the electric field in time, that's also going to contribute some current to the previous equations that we saw. So in order to complete Ampere's law in a time varying case, we actually have one more current we can see, and we'll look at that at the very end. And the classic example of that current is in the capacitor, right? So that is kind of the story of the next 2 weeks. So we're going to do 2 homework assignments, homework assignment 7 and 8 on electromagnetics. We're going to have a review on November 2nd when the homework aid is due. And then the next exam is on November 4th. Okay. So what is that? Two weeks from Thursday is when the next exam is. In addition to this electromagnetics, looking at this Faraday's law, right, the project, which I will introduce in all details, and I will upload the documents related to the project on Thursday. We will look at that in more detail, and the project will be a project related to Faraday's law, so an application of the Faraday's law in the electromagnetics, and you'll work on that. You'll have this week all the way until the final report will be due during the finals week. Okay. So any questions about that? All right. So the only thing that I'll add is, this is after exam 2, but the first exam 1 and exam 2 are very closely related to each other in terms of the material, like first the electrostatics, then the magnetostatics and electromagnetics, like the whole time varying field. And then the final section of the class. So basically after exam 2, we'll switch gears a little bit, and all of this stuff is likely to be brand new to you. So this, the work that we do after exam 2 is all on transmission lines. And the way that this will relate is that we had all these time varying fields that we looked at before. And after exam 2, we're going to look at how do those time varying fields, or any field, how do they propagate on a transmission line. And transmission lines are things like coaxial cables, microstrip lines, basically anything that you've ever used to carry the electronic information. We'll consider how that works. Okay. And this stuff, the transmission line theory, is what I find to be the most interesting part of the course. So that's what we'll do after the exam 2. All right, so that's a bit of an overview of this. So let's get going. Also, I did make, so the the homework 7 is available on the Moodle page, and you should all be able to see it. So we're going to do, there's several problems. We're going to work through the examples in the book. Okay, so if you have the textbook, we're going to work through these examples. In some cases, I show you like a slightly different approach to the textbook. But there's both these examples, example 6.1, 6.2, and 6.3 are shown in the textbook, and we're just going to look at them in more detail. And then the last two problems, 6.1 and 6.3, these are problems right from the back of the chapter problems from the textbook. Okay. So let's start with this one. Okay, so we have an inductor that's formed by winding n turns of a thin conducting wire into a circular loop of radius a. So that's what's shown in this drawing, right? So we can imagine, right, that this wraps around n times. So when we're applying Faraday's law, there's a common assumption that we'll make. Okay. Is that these n turns are very tightly wound. Okay, and what this means is that the loop is very thin. Okay, so if we're looking at this from the side, right, where we have all these loops, okay, we're assuming that this is very thin and basically negligible distance. So we have this n turns, and we're assuming that they're very tightly wound, so tightly wound that it's a very small distance. And this means a couple things. One, right, this means that if we have a field, the reason that we assume this, right, is if we have a field like this, we're assuming that none of the field goes through these, right? Like you could imagine some goes through the cracks in between the windings. And we assume that this part does not matter. Okay. We assume it doesn't exist. So we're assuming that the windings are so tight that all of the field goes through the entire stack of windings, and that we don't have any field that's just partially impinging on the winding. That's the reason for this. It simplifies a lot of the work. Okay, so the loop is in the XY plane with the center at the origin. Okay. So if the loop is on the XY plane, what's normal to the loop?
The z-axis.
Yeah, so the z-axis, right, we'll just keep this in mind, but this one is normal to this whole loop. Okay. And these windings, they're all connected up, and in the windings, they have, at the beginning and the end, they're connected via a resistor R over here. Okay. And it's in the presence of a magnetic field. All right. And what we can see, right, is for the first time we have a magnetic field and we have directions, but we also have this T, right? So this is a time varying magnetic field with omega being the angular frequency. All right, so this is the problem setup. And there's one more point that I want to make is that we've said that the inductor loop is in the XY plane with the center at the origin and it's connected to the resistor R. One of the other things that we will always assume, or basically always assume unless told otherwise, is that the wire has no internal resistance, okay? All right, so this means that this, this section of wire from here to here, we assume that the resistance is equal to 0 right here, right? There's no, we assume that there's no actual resistance in the wire at all. Of course, in real life, wire does have some resistance, right? And if you decrease the conductivity of the wire, that would increase the resistance. Or if you make the wire smaller, right, smaller gauge of wire, you might also increase the resistance. But in this case, in these problems, we will assume that there's no internal resistance on the wire. So all these sections of the loop don't actually have any resistance. And that any resistance in our problem is either going to be given as a resistor that's linked to looped coils, or is specifically described in the problem statement such that it says, the wire has this much internal resistance. Okay. Okay, so this is another assumption that we'll make in these problems. All right, so the first thing that we're asked to do is to find the magnetic flux linking a single turn. Okay. All right. So the magnetic flux is this capital phi. All right. And this is given as the B field dot with ds. All right. So take a minute and see if you can determine what this magnetic flux is going to be. All right, so we know what the field is from this. So see if you can compute this integral on the flux. All right. So take a minute on your paper and work this integral. All right, and if you need a hint, right, we should use this DS. I'll give you a few more moments, and when you have an answer, upload it to the Google Drive. All right, so I have a couple answers. Let's take a look at this one. All right, so anyone else get this same final result?
Yes.
Okay. All right, I think, yeah, that looks what I got. So let's look at this, make a couple notes. All right, so first of all, oops. At this point, right, make sure the notation should still be clear, right, that this is the dot product, right? These two vectors, it's not an actual continuation of the of one vector, but this is actually, there's still a function that it's a function or a computation that we need to perform here between vector 1, right, and vector 2. All right, so I think it looks like here the notation's back, so that's good. All right. So, right, when we take the dot product between these two vectors, right, this vector, right, has no y component, so we should lose that when we go down here. So that's what this looks like. So good job. And then let's see on this, right? How did you choose the limits on this? Because is this Mario's work?
Yeah, that's mine.
Okay, so would you like to describe how you chose the limits?
So for the radius, we're told that the radius is A of the magnetic, the turns of the inductor, my bad. And then just the phi is just, obviously it goes around in a whole circle, 2 pi.
Perfect. Yeah. So Mario, he chose the limits, right? We wanted to find the field that goes through that whole surface. So Mario, he chose the limits so that the limits would integrate the entire surface contained by these loops. So he started from the R0, went all the way out to A, and then went all the way around, right? So that this whole coil was integrated over. So that's how I chose the limits, right? 0 to A on R and 0 to 2 pi here. Went through this, the integration, right? And arrived here at this magnetic flux. Okay, does anyone have any questions on this? All right, so the only other thing that I want to point out is that typically, right, we will have, in a time varying field like this, right, this field is governed by sine omega t, right, and sine, right, sometimes it's positive and sometimes it's negative. Yes, so sometimes this field is pointed this way, and sometimes it's actually pointed this way. Does that make sense? So it's actually, that field is going, it's changing in time, going up through it and then back down through it. And what you want to do is take your right hand, okay, and the direction that if you point your thumb in the same direction as your ds, okay, so we chose this ds, right, with the z in the positive direction. So if you point your thumb in the same direction as the ds you chose, your fingers are going to curl, right, and that curl of your fingers is going to define your polarity. So in this case, right, we chose the ds to be in the positive z, and so our fingers curl in this direction, and so you can see that our fingers curl from plus to minus. So that's how we're choosing the polarity of this V EMF. Does that follow? Do you understand why this is important? Depending on what's happening to the B field in time, this voltage is either going to be positive or negative, and so we need to choose a reference for it. So just like many things, right, especially voltages, right, we always need to consider a reference in our system, and the system reference in this case will be determined by the contour that we've chosen. So just keep that in mind, because that will come up in the other problems.
So we can't say the B field is going in the Z direction.
Not all the time, right? So, well, okay, let me back up. It is always in the Z direction, but it might be positive Z or negative Z. So let me, all right, so our B field it's like this. So we can rewrite this as okay, in this part, right, let's just ignore it for now, right? This one does not contribute to the flux. This part of the field does not contribute. Right, because this part is in the, it's tangential. Oops. So let's focus on this one only. So this is some constant. So the amplitude is 3 B naught at the maximum. And this amplitude, right, it could be the largest possible. So the largest B that we could make would be in Z 3B naught. Right, does this follow? And the smallest, oops. Okay. Okay, so sometimes this field will be pointed, sometimes the component of the field that's going through our coil, sometimes it will be pointed this way. This is the largest it could be. And then the smallest it could be is this. And this will change in time, right? Just like because our field is changing in time. So as a reference for all of the time, right, we chose this as the reference. So let's see here. Right, and these fingers curl from plus to minus. So later, when we get to the final VEMF answer, we'll always reference it like this. So whenever the field is in that, whenever the, yeah, when the field is pointed in that direction, we'll get a VEMF that's also positive. But later on in time, right, as time goes on, the field is pointed up, then it's pointed down. Eventually, as time passes, right, the polarity of the voltage will actually be different. And so the total voltage across this coil, right, is going to change in time. Sometimes it'll be positive and sometimes it'll be negative. But when we say it's positive, we're just referencing it to the flux that we chose. So let's keep going on, and I think this will become more clear. Okay. But do you have any other questions before we do move on?
No.
Okay. All right, so now let's find the transformer EMF. Okay, and then who knows why does it say transformer EMF? So what are the two kinds of EMF that we have from the videos that you watched? Who remembers? So one of them's obviously transformer EMF. What's the other kind of EMF that we can get? Did anyone watch the videos?
Is the emotional?
Sure. Yeah, that's correct. So we have two types of EMF. So electromotive force. We have the transformer and the motional. So this one is due to changing magnetic field, time varying magnetic field. And this one is due to changes in the loop size or movement in the loop.
Under what conditions would the loop size change?
Let's see. Usually, I mean, it's kind of hard to imagine how the loop size could change, because usually our loops are fairly fixed, but sometimes, right, you could have a circuit, let's say like a circuit, I don't know, that has a right, you could open this up and the loop would be all of a sudden become twice as big. So that might be one circumstance. It's a little bit contrived, but change in position also. This is much more common, right? This is the normal one. Oh, another one. Yeah. Okay. Change in loop size. Actually, let me just erase this, because the best example is like a rail gun. Okay. Right. So you have two prongs, and then you have a bar, right? Conducting bar. And if you move the bar, if you slide the bar, right, the loop size is going to change. So this is probably the best real world example. And then the other common way is like if you have just a series of loops, or a loop, and you spin it, right, around. This is the most common way to change, and often this will be spinning something radially. Okay, so we have two types of the electromotive force: the transformer, due to the time varying magnetic field, and then the motional, due to the loop changing, the loop itself moving in time. So both of these describe changes that can happen in time, right? So change in time, or change in time. So change in time of loop size, or change in time of position. But all of these, right, mean that we're dealing with a time varying system. So we could have a time varying system due to the magnetic field, or a time varying system due to the loop. And of course, we could have both a time varying B field and a time varying loop size, which would mean that we could find both a transformer and motional component. But this case, right, in this one, is this loop moving at all in time? No, we don't see anything about this loop moving in time, right? There's nothing to describe a change in the loop radius. There's nothing to describe a change in the loop motion. The loop is just totally still while this magnetic field changes in time. So for this problem, right, we have the VEMF equal to the transformer EMF and the motional EMF. And we don't have any loop motion. There's no loop motion at all. So all of the electromotive force is going to be due to the motion, the change in the magnetic field. Okay. And so we can describe this then. The relationship will be between the number of coils and the derivative in time of the flux. Okay. So the transformer EMF, which we're asked for, the transformer EMF is going to be given by this equation. Okay, so you've learned the problem gives you a few more variables. Right? Let's see here. Paste these in. So based on what we're given, find an expression for this EMF voltage. All right, so work that on your paper. So see if you can find this derivative and find a numerical expression for the transformer voltage. The only variable that will be remaining, right? Only one variable will be left. Do you know which variable it will be?
Your time.
Yeah, just the time. So find a numerical expression for the EMF voltage with just that one variable, the time variable. All right, so in the interest of time, let's see, 3 omega pi a squared b naught, or n cosine omega t. Did anyone else get that?
Yeah, I got that.
Yeah, so right, this is constant, this is constant, this is constant, this is constant, this is constant. So we just really need to take the derivative of sine omega t. We'll get cosine omega t. And then when we plug this in, what we have is, I got 188.5 cosine 10 to the third t volts. Okay. So now we have an expression for the transformer EMF. Does this look correct to you? Okay, hopefully it does. Now let's look at this a little bit more. And as we mentioned, right, there's this idea of polarity, and that's what the part C asks. It says, what's the polarity of this at a given time? So we have, let's see, pull this down. Okay, so let's find the polarity of this at time equals 0 seconds. And so this is basically Lenz's law. And there's two ways that we could think of this. All right. So the first is, let's look at the based on Lenz's law, right? We have this d phi dt. And if we evaluate this, right, at t equals 0, this will give us information about our polarity. Okay, so at t equals 0, what is d phi dt? Is it positive or negative at time 0?
It would just be that negative 188.5.
Yeah, and let's see. And we're actually only even dealing with this part, okay, just the phi. So maybe so we aren't even dealing with the the negative n. Just this part of the derivative is what we care about. So at that time, right, if we look at that derivative at 0, at time equals 0, and evaluate this, it's going to be larger than 0, this part. So this part of the equation is larger than 0. And so then if we consider the EMF, we have two parts, right? Part 1 and part 2. So if this part is greater than 0, then that means that you're going to modify this, because n is always, this must be a real positive real integer, right? And the number of coils that you have, this must be, n is going to be 1, 2, ... to n, right? So if the derivative of the flux is greater than 0, then you're going to modify it with a negative number, meaning that the VEMF is less than 0 at time 0. Right. So if you evaluate the derivative of the flux at a given time, this minus n is going to then modify that derivative and tell you whether or not your EMF is greater than 0 or less than 0. Does that follow to all of you?
Question is, why don't you just substitute T for 0? Or 0 for T.
Into here?
Into the VEMF we already got.
VEMF. Okay. And that is because one of the things that we're dealing with here is this idea of Lenz's law, which tells us that the VEMF is going to be related to the current, which always opposes the change. Okay, so there's always going to be opposition to change in the system. And so the other way that we can think of this is that, right, in our system at that time, so we have our B field, which is sign related, right? So at time 0, B is increasing. Okay. And therefore the current, the induced current, right? The current I must create a B induced in the minus Z. So if you have a magnetic field that's increasing in the positive Z, right, that's going to make a current. And that current must create a B induced that opposes this change, right? So this is the field and it induces a current. And the current must create another induced field that opposes it, right? So if the field is going up in Z, you need to have, and it's increasing, you need to have a induced B in the minus Z direction to oppose and balance that change. That's in minus Z. So that means, right, if your B induced is opposed, then your current must go from 2 to 1, right? So put your hand up like this and your fingers, right? Your fingers point down and that's in the direction of B induced. So you have your field here, which is increasing, and then your fingers are pointed as the field is increasing, your fingers are pointed in the induced direction that opposes the change. And your thumb, which direction does your thumb point? Does it point from 2 to 1 or from 1 to 2?
One.
Okay, so my thumb, my fingers are down, and my thumb is as it's pointed, it goes, the thumb direction goes in like this, okay, from 2 to 1. So your thumb points from 2 to 1. Okay. And 2 to 1, right? This is backwards, right? We defined based on our Z, our DS, which was in the positive Z, right? We made a DS in the positive Z, which we referenced as plus to minus, but our thumb is pointed at the opposite direction. So our thumb points from the 2 to 1, which is from minus to plus, and this also indicates negative polarity. So I think our time here is up, but just realize, right, let me extend this a little bit. Right, this means there's 4 regions. Right, in this case, in region 1, B is increasing in Z, okay? In this region, oops, this is region 2, and it is decreasing in positive Z. This is region 3, and this is decreasing in negative Z, or you could say this is increasing in a negative direction. And then in this region, right, it's increasing in the minus Z direction. And so each one of these regions is different, and this induced current must always oppose the change. So the change is always opposed. That's why mathematically we look at this, right? This is the derivative of the flux. This describes the change, and the transformer voltage always opposes this. So do go watch the videos, especially the ones that I created. Those are the ones, the additional videos on Lenz's law. I go into much more detail on those. So check the, where is it? I'll show you real quick. Check these additional Faraday's law videos, and this is a series of videos that will help you understand this better. All right, well, I will see you all on Thursday, and feel free to take off now if you have any questions. I'll stick around and answer them.
Dr. Chrysler, so you mentioned doing the quiz on Thursday. Would you like email me a new one just before the time?
Yes, okay. Yes, on this week on Thursday?
Yes.
Okay. Yeah, let's do it right after class. Does that work?
Okay, that works too.
Okay. All right, that sounds good. All
Thank
right,
you.
so just remind me on Thursday. I'll go ahead and do that.
Okay.
All
Thank
right.
you.
See you then. All right, bye.